All right, so what I want to do today is wrap up chapter 2. We have two small topics remaining. One is source transformation. The other one is maximum power transfer theorem. Source transformation is a technique that is derived from Norton and Thevenin circuits. And then maximum power transfer is a topic we cover. It's a big part of the lab. Okay, so cover the topic in brief in class, and then we'll go into chapter 4. So, switch out section 4, chapter 2. Next. So we covered the concept of Thevenin and Norton equivalent circuits, where we described a large linear network in terms of either a voltage source or a current source, right? So we can take a large network, describe it as a voltage source, then we describe it as a current source. So if A equals X and B equals X, we can state that A equals B. And that's where the concept of source transformation comes from. If you have a voltage source in a circuit, you can convert it into a current source and vice versa if certain conditions are met. Like Thevenin circuit is a voltage source in series with a resistor. So if you have a circuit that meets those conditions, you can convert it or transform it into a current source in parallel with that same resistor. The equation, of course, is given by Ohm's law. VTH is IN times RTH. And that's it. That is source transformation. You can convert a voltage source into a current source and current source into a voltage source if those conditions are met. Now, the reason for doing this is sometimes there's a mix of current and voltage sources in a circuit. So sometimes or oftentimes it's useful to simplify a circuit. And we'll look at an example in the next page, the next slide. So we would take a voltage source, convert it into a current source, or a current into a voltage source. And then instead of applying techniques like node voltage analysis or mesh current analysis, we can simply solve it using Ohm's law, KVL, and KCL. Okay, that is the purpose of using source transformation. But source transformation is not that easy. It's a little tricky to do because we have to recognize the nodes where the sources are connected. So in this example, in figure A, you can see a voltage source as well as a current source, right? Voltage and a current source. If you were to solve this circuit, meaning trying to determine the voltages or currents, we would have to apply either superposition or node voltage analysis or mesh current analysis, right? Multiple sources. So we will see how we can solve this using source transformation. The current source and the voltage source are connected at this junction right there. All right. Again, this is a very simple circuit. Other circuits are far more complex, right? I'm going to call these nodes A and B. Top node is A, bottom node is B. And you can break it apart into two pieces. And the reason I said it's tricky is because we have to be careful the nodes where we break the circuit. So this is A, this is B. That's the voltage source on the left. That remains as it is. R1 also remains as it is. And then on the other side, we have the remainder of the circuit. The remainder of the circuit has a current source in parallel with that resistor. Right? So we have a 1 amp, we have R2, 10 ohms. Now, If we wish to transform this, we separate it out. So meaning let's look at the right side first. We took out the current source and there is a resistor in parallel. So we can say it is a Norton equivalent, right? And if it is a Norton equivalent, we can transform it into a Thevenin equivalent. We change this, keeping these terminals in mind. So we have A and we have B. The current source is now changed into a voltage source. And the resistor is now in series. The resistance value remains the same. So it's R2 with a value of 10 ohms. The voltage source is given by V equals IR. I is 1 amp, R is 10. So the voltage source has a value of 10 volts. And then you plug it back into the circuit exactly the place where it was disconnected from. And that would give us circuit B, or circuit shown in B. Okay. So current source is transformed, you get B. Voltage source is transformed, you get C. Right, let's take a 10-second pause while you write it down. Let me know if you have any questions. Yes. I will explain. Okay. All right, so now you have two voltage sources in the circuit, right? Without overcomplicating things, what is the relationship between R1 and R2? In series, you can combine them, right? So you get one single resistance, 15 ohms. And you have two voltages in there, 15 ohms, simply apply KVL. You apply KVL, you get the resulting voltage across that resistor. So you can solve this in one step by applying KVL. 20 minus 10 gives you 10 volts. Left side is higher, right? Right side is lower. So you got 10 volts across that 15 ohm resistor with a plus on the left, minus on the right. That's it, as easy as that. You got 10 volts across 15 ohms, you apply Ohm's law, you can find the current that is flowing through that 15 ohm resistor. Okay. Then you can, once you have the current, you can split it up and determine the voltage across each of those resistors. Then you can determine power and you can determine energy, everything. So instead of doing node voltage analysis or mesh current analysis, a simple application of Ohm's law and KVL. That's it. So as I said, it makes the analysis much easier, but setting up is very tricky. Because if it's a large circuit and you have a source and a resistance in the middle of the circuit, which happens all the time, if you wish to transform that, you have to take it out of the circuit and you transform it and you plug it back into the same place. And that sometimes is not easy to do. Okay, not easy to do. All right, any questions? Okay, let's look at the other side. So if we take the voltage source and we change that into a current source, direction, of course, for a source goes from minus to plus. So the current would be going up. And at this time, my voltage source, sorry, my current source will have a resistor in parallel. Resistance remains the same, R1, 5 ohms. I is V over R, so 20 divided by 5 gives me 4 amps. And you plug it back into the same circuit, you obtain figure number C. Yes. The question being asked is this cut. We need to satisfy the conditions for Thevenin and Norton. So the voltage source must have a resistor in series. What is on the other side? We actually don't really care. This is a simple circuit, but there could be multiple resistors and multiple sources on the other side. The only thing we care about is the voltage source, and it should have a resistor in series. So I took that apart. And if I was considering the Norton, which is on the other side, the only thing I care about is it should have a resistor in parallel with that current source, because that would give me a Norton circuit. And then what is on the other side, I don't really care. And so that's the point where I would disconnect it. Make sense? Right? Okay. In this case, of course, again, the circuit is chosen such that it breaks up exactly in equal parts. But large circuit could have multiple different components in the middle. Okay, circuit C, you have two current sources, apply KCL, you can find the total current going into those resistors. You can again find Req, right? Two resistors in parallel. So you find Req, apply KCL, total sum is 5 amps plus 1. 5 amps is being split between 5 and 10 ohms. That's it. Apply current division, one-step answer. Or you can apply Ohm's law. So again, instead of doing superposition, node voltage analysis, or mesh current analysis, just simple application of the 3 laws. So source transformation, there's just a extra credit tutorial on the homework, but there's no other problem. But as a concept, this is something students should be familiar with. We are required to teach it. And so I have one slide devoted to it. Okay. Then the next topic is maximum power transfer theorem. So electronic devices often are comprised of multiple cascading stages of different circuits. I like to use the example of an audio video receiver where you would have a preamplifier stage, more commonly known as a preamp. The output of a preamp is connected to the main amplifier stage. And the output of the amplifier stage is connected to a speaker. Okay, connected to a speaker. So maximum power transfer states that in order for maximum power to be transferred from the first circuit to the next, the Thevenin resistance of the first circuit should match the load resistance of the next one. Essentially, the Thevenin resistance of both circuits should match up. Okay, so here is a sealed box representation of a two-terminal circuit. That circuit can be represented by its Thevenin equivalent network as a voltage source in series with a resistor. RL simply notes that it is the load resistor or simply the load. Every succeeding circuit is acting as a load for the preceding circuit. So the speaker is the load for the amplifier. The amplifier is the load for the preamplifier. Make sense? Right? So every succeeding circuit, meaning if you take the preamplifier and the amplifier, if you want maximum power to be transferred from the preamp to the amplifier stage, the Thevenin resistance of both should be equal. Okay, Thevenin resistance for both should be equal. In that scenario, maximum power will be transferred. There's a small derivation, but no need to do that derivation. RL is simply described as equal to RTH. You can use that equation to determine current IL to the load resistor. Power is given by the equation V square over R. When you plug that, when you plug the values into that equation, you obtain PL max is VTH square over 4 times RTH. This is the equation you will actually use in the lab. V square over R. Okay. Important thing to note is maximum power does not translate to maximum efficiency. Okay. Sometimes you want max efficiency, sometimes you want max power. As an example, as an analogy, I would use a vehicle, electric vehicle or a regular ICE vehicle. Okay. If you're driving on the highway at, let's say, 40, 50 miles an hour, you would obtain maximum mileage. But that is not the point where you get maximum power or maximum speed. In order to get more power or more speed, you would burn more fuel. Burning more fuel would be inefficient, but you would get maximum power or you get higher power and higher speed. Make sense? Same thing with electrical circuits. Maximum power does not translate to maximum efficiency. Depending on the use case scenario, sometimes you want maximum power, sometimes you want maximum efficiency. Electric vehicle would actually use this technique because you have a battery which has a finite energy resource, right? If you want maximum power, you're going to consume a lot more current coming from the battery, uses it up. If you want to run for longer, if you drive for longer, you want maximum efficiency, meaning maximum energy from the battery should be transferred to the wheels, to the electric motor. That way, the mileage for the battery would be much higher. So again, depending on how you're driving that vehicle, sometimes you want maximum power, sometimes you want maximum efficiency. Let's see what else. That about covers everything. Chapter 2. Chapters 1 and 2 are the most important for circuit analysis. This is where you learn all the techniques. Okay. If you think about it, and I summarize this, there's only 3 actual equations that we learn: Ohm's law, KVL, and KCL, and that's it. Everything else is derived from these 3. Okay, these are the only 3 equations that you need to remember. Current division, voltage division, derived from Ohm's law. Node voltage analysis is an application of Ohm's law and KCL. Mesh current analysis is an application of Ohm's law and KVL. Thevenin and Norton is a concept. It's not an analysis technique per se. It's a concept. You apply all the techniques you learn to develop that concept and to apply that concept. So again, chapters 1 and 2 are very important. You learn all of these techniques and these concepts. The 3 equations that you need to remember are Ohm's law, KVL, and KCL. Everything else is derived from these 3. It's a setting up of the problem, understanding the problem, and applying the concept. That's the most important. All right. Yes. That's not the Thevenin. That's not how it equals. It's a condition that must be met in order for maximum power to be transferred. So there is a small derivation. Typically, we don't do it for non-E major classes, but we derive the equation and then we set the equation to derive PL max. And when we set it to derive PL max, then the result is that RL equals RTH. So the result of that derivation gives us RL equals RTH. Okay, so good question. The question being asked was, how is it RL plus RTH? Yes. There is no, so this is RTH actually. It's RT. It's not quite visible. So that's RTH, and this is VTH. Yes. That's when maximum power is transferred. So there were several students are in different lab sections. So there were several comments on the feedback about how the lecture is behind or the lab is ahead of the lecture. So I'd like to clarify that. According to the normal sequence of classes, our class or the material that we're covering is completely in sequence. We are actually 1 week ahead of the material because lab 4 is not scheduled until the next week for most of you. But we always, every quarter, we have like a Monday that is, that is a holiday. So that's coming up on May 27th, I believe, like Memorial Day. It's almost the end of the quarter. But the following Tuesday is a Monday schedule. So we lose that Tuesday. So if your lab is on a Tuesday, some instructors, in order to cover all the material, started 1 week early. So if you start 1 week early, you're 1 week earlier in the quarter that you're doing that lab, meaning lab 4 was already done this week for, for those lab sections. To compound that, to make it even, make it even earlier, is that the lab takes place earlier in the week. So if it takes place on a Tuesday, you only have like 1 class on a Monday to actually cover that Tuesday, if that makes sense, right? If it's later in the week, if it's on a Thursday or on a Friday, you might have 2 lecture classes. But if the lab is earlier in the week, it compounds the matters and makes it even worse. So not only are you 1 week ahead of all the other labs, your lab is also ahead in the week. But for that reason, that specific reason, the lab write-ups are detailed. There is an introduction, there's a background section, and it has equations. As most students actually do not read that background section in the lab write-up. But this is the reason why they are detailed. So the labs and the lectures are supposed to complement each other, but they do not supplement, kind of supplement and complement at the same time. Okay, but students are supposed to study for the lectures and the labs independently. So whether your lab is in sync, whether it's ahead or whether it's behind the lecture, students are expected to study for the lab a little bit separately, and the background section in the lab write-ups do help with that. The equations in the lab write-ups will help you solve for all of the pre-lab problems. Okay, so if you have not been doing that, please go ahead and do that too. Do not just solely rely on the lectures. You have to read about the lab separately. Let's see. That's about it for chapters 1 and 2. So now we'll get into chapter 3 and then chapter 4, where we'll talk about capacitors and inductors. Okay. Any questions before I move on? Okay. Yes. Yes. So the question being asked is, how would we split up if we wish to perform source transformation on a large circuit? How do we split it up, right? Now, there may or may not be a current source in the circuit. There could be like maybe hundreds of voltage sources. It doesn't matter whether it's a voltage source or a current source. If we wish to split up a voltage source, you're absolutely right. Yes, we have to maybe draw 2 lines and cut it out. We might even have to draw 4, because if the voltage source is in the center with components on all 4 sides, we have to figure out where it is connected in the circuit. And that's why it's tricky. Sometimes you may think that the resistor is in series, but it may not be in series. You have to keep in mind, series connection requires only 1 junction and no more than 2 connections at that junction. So if that condition is met, then you can cut out that voltage source and that resistor. Then we mark the nodes where we cut it out. we transform it outside of the circuit, and then when you plug it back in, you now have a parallel connection of a resistor and a current source. You plug it back into the circuit at exactly the same two nodes. That's how you would do it. So it doesn't matter whether it requires like 2 cuts or 4 cuts. We have to keep track of the nodes and then remove it from the circuit. Okay. All right. Chapter 3 then. So chapter 3, inductance and capacitance, or inductors and capacitors. Inductors and capacitors, unlike resistors, are energy storage devices. They are energy storage devices. Like a resistor, they are both passive components, meaning they have no energy of their own, but they do have the capability to receive energy, to store it, and then release it back into the circuit at a later period in time. Okay. So again, they are energy storage devices. They can store energy and then return it back into the circuit at a later period in time. Now, when we say later period in time, that time could be like seconds, days, weeks, months. But that would be like a infinite, not infinite, but a huge inductor or capacitor. Typically, electronic circuits, it is usually in the order of a few seconds or microseconds or nanoseconds or even picoseconds, very small, very, very quick. Nevertheless, it still requires a finite amount of time. Okay. So resistors receive energy and dissipate it as heat. Electrical energy is converted to thermal energy. There's some heat loss in inductors and capacitors also, but primarily the energy is stored. For an inductor, the energy is stored in the magnetic field. For a capacitor, it is stored in an electrostatic or electric field. Okay. We won't go too deep into the physics of things, just barely skim the surface. We'll stay on the engineering side of things. Okay, so we'll talk about what a magnetic field is, and we'll begin there, but we won't go into the physics. From what I understand, your physics 3 classes do cover inductors and capacitors to a certain extent, hopefully. So if you have not yet taken physics 3, which I guess with some students it is a possibility, or you might be taking it concurrently, you will learn about inductors and capacitors anyway. Okay. So inductors and capacitors, we will look at in chapter 3, we will look at the equations, the general equations that govern the physical quantities, the voltage, the current, the power, the energy for the inductor and the capacitor. Okay, that's chapter 3. Those would be the generic equations. Then in chapter 4, we will look at a small portion of that analysis. Now, when I say small, I'm not saying the chapter is small or the equations are small. I'm referring to the energy transfer phase. Okay. So remember, I said a source will supply energy to the inductor or the capacitor. The inductor capacitor stores the energy and then transfers it back into the circuit. That energy transfer does not take place instantaneously. Okay. Thanos does not snap his fingers and transfers the energy. Does not work that way. That energy transfer takes a certain amount of time. And that time depends on the size of the inductor and capacitor. The analogy I like to use is a bucket. If you have a bucket, you're trying to fill it with water and then emptying out the bucket later on. The filling up the bucket will depend on the size of the bucket, the flow of the water, as well as the dimensions of the pipe. The larger the bucket, the longer it's going to take to fill up, the longer it's going to take to empty it out. The slower the flow of water, the longer it's going to take to fill it up. The smaller the pipe, the higher the resistance. So transfer it to an electrical circuit. The larger the inductor or capacitor, the more energy it can store, the longer it takes to fill up. The higher the amount of voltage or current, the faster it will fill up. And of course, the higher or smaller the resistance, the slower or fast the energy transfer. In chapter 4, we will look at the equations that govern the energy transfer phase. Okay, so the energy transfer takes place in microseconds or milliseconds, very, very fast. but we will look at the equations that will describe the charging or the energy transfer and discharging phase. So that's why I said a small portion. Okay, so let's begin with an inductor. I said inductor stores energy in the form of a magnetic field or associated with the magnetic field. So let's look at what a magnetic field is and how it will store that energy. So magnetic field is based on, not based on, is associated with the phenomenon known as magnetism, right? Magnetism. And magnetism plays a very important role in every electronic device and every electric circuit we work with today. Generators, transformers, they're all based on the principles of magnetism. Generator, an electrical generator is nothing but a coil of wire that is rotating inside a permanent magnetic field. That coil of wire is rotated using mechanical energy, wind power, or water power that rotates the turbine. The turbine is connected to an electrical coil. That coil rotates inside the magnetic field, and it generates electricity. Okay, so magnetism is an important part of everyday life. Some of the not common examples, some of the most famous names that did research in electromagnetism are listed here. We have Ampere, who first published his Ampere circuital law that covered equations governing voltage, current, and magnetism. And then following his work, we had Michael Faraday, Carl Gauss, James Maxwell, who all did research. These researchers, and there were several hundred other researchers who are unnamed and lost in time, but they all collectively contributed to the field of electromagnetism, right? Electrical engineering and electromagnetism. The ones that become famous are the ones who published first. And if they publish first, they become famous and they get things named after them. And so you have Michael Faraday. His name is associated with the units for capacitance, farads, right? Ampere, of course, is the unit for capacitance. Maxwell's equations are, the founding principle of like electrical engineering, for that matter. So if you talk to any EE student, they'll tell you Maxwell's equations, how important they are to the field of electrical engineering. Transformers, these are not Michael-based transformers. These are based on the principle of mutual inductance. If you take two inductors, two coils, and you wind them together, the magnetic fields of both inductors get connected and interlinked. Energy is transferred from one end to the other. And they are the reason why we can transmit electrical power supplies over long distances. You can easily step it up and step it down in levels. A common example I like to use is your smartphone devices if it's capable of wireless charging. If you have ever taken a smartphone with wireless charging capabilities and placed it on a charging plate, wireless charging plate, you are using the phenomenon of mutual inductance. Your smartphone on the back has a coil. That coil is an inductor. It has a magnetic field. You place it on a wireless charger. The charger also has a coil. That also has a magnetic field. When you place it in close proximity, if it gets close enough, the magnetic fields link up. When they link up, the energy from the wireless charging base is now transferred through the magnetic field into the magnetic field of your smartphone, which is then converted into electrical energy. Yes. There are lots of equations and a whole chapter in EE that governs all of this. If we have time at the end, I'll cover that. Yeah, so it's known as mutual inductance, and it's basically two coils on either side, and it links together, and there are lots of equations that go on that. So that was a good question, though. But if you're interested, I'll do a whole chapter on that. The question being asked was about, how it actually works. But anyway, I like to give like real life examples of where it's actually used. So that's where it's used. All right, so magnetic field. Anytime you have a wire, it inherently has resistance, inductance, and capacitance. Okay. If I take a cable like this, like HDMI cable or this power cable that is carrying, power from the power outlet into my adapter, Whether the power outlet is live or not, that wire has resistance, it has some inductance, it has some capacitance, but it is so small, you cannot even measure it. And the level, the value of that resistance or the inductance or the capacitance does not rise to the level of interference. Meaning, I could take the 6-foot long power cable, plug it into the power outlet. Its job is to convey 120 volts from the power outlet into the adapter. It has resistance, but it does not interfere with its current carrying capacity. 120 volts is still being transferred 6 feet away. Same way you have inductance. Inductance does not rise to the level of interference. But anytime current passes through a wire, a magnetic field is established across that current carrying wire. That magnetic field has flux lines. The flux lines are basically are what comprise a magnetic field. The flux lines are continuous. There is no beginning and there is no end. Okay, but it is wound around that current carrying conductor. And the direction can be given using the right-hand rule. So next time you plug a charger or an adapter into your power outlet, if you wrap your palm around that wire and you extend the thumb points towards the direction of the current, meaning away from the power outlet, and your fingers point in the direction of the magnetic flux lines. So the current would be the thumb, and the magnetic flux lines would be the fingers, finger direction. Now, this establishes a magnetic field, but that magnetic field is very weak, right? If I stick anything to this live wire right now, nothing's going to stick because you have insulation around it, right? It's not bare. Plus, the magnetic field is going to be very weak because of that. If you take that same current carrying wire and you wind it up in a loop, all the flux lines around that wire get aligned and they point out from the center of that loop, right? You had flux lines that were going in this direction, you wind it in a loop. Now the flux lines are going into the coil and out through the center of that coil in one direction. If you take that same wire and you wind it up into multiple loops, you will establish a magnetic field that is similar to a magnet. It'll have a north and a south pole. The magnetic flux lines will align, and now the flux lines will flow through the center of that coil, or the center of that entire coil. The center of that entire coil, the spiral coil, is known as the core of that coil. Okay. Again, the field is weak. It is not strong. It is weak. It, of course, also depends on the amount of current that is flowing through that wire. Researchers discovered if you pushed a magnetic material through the center of that coil, meaning through the core of the coil, you can make the magnetic field stronger. The reason is, the definition of a magnetic material is, it allows or permits the establishment of the magnetic flux lines through the material with ease. Okay, so magnetic material is one through which you can easily establish a magnetic flux line. Some materials are magnetic, some are not, right? So if you push a magnetic material through the center of that coil, center of the core, the magnetic field can be enhanced. The strength of the magnetic field is enhanced and becomes stronger. And that is also the working principle of an electromagnet. All right, you may have seen or remember pictures or videos where these big cranes can easily lift up like heavy vehicles in a junkyard, right? It's a brilliant application of an electromagnetic principle, right? You have a material that is non-magnetic. You have current flowing through that material, wound around it. You flip on a switch, current starts flowing. When current flows, magnetic field is established. Due to the presence of the magnetic material, that field is very strong. It is so strong, it can now attach to metallic vehicles and lift it up with ease. You flip the switch off, magnetic field turns off, and it drops. There is no other thing needed to do. You don't have to have a hook. You don't need to attach anything to it, nothing, right? It's brilliant in its simplicity. So again, that's the working principle of an electromagnet. You're simply taking an inductor, you push a core through it, a magnetic core through it, run a current through that inductor, it becomes an electromagnet. So a current passing through a coil, a magnetic coil, establishes a magnetic field. That component is known as an inductor. It is symbolized or noted with an uppercase L. All the symbols are uppercase. Resistor, inductor, and capacitor, R, L, and C, they are all uppercase. The units are also uppercase. The unit for inductors is named after me, uppercase H, not really, named after Joseph Henry, okay, American physicist, a long time ago. Again, uppercase H, uppercase A for amperes, uppercase farads, F for for capacitors. So again, RLC, everything uppercase, units also uppercase. It is a passive component, meaning it follows the passive reference configuration or the passive sign convention. Okay, meaning if current flows in one direction, then the point of entry of the current is plus, point of exit is minus. When current is applied to a inductor, when current flows to an inductor, a magnetic field is established, a voltage is established across that inductor. The voltage polarity follows the passive sign convention. Okay, point of entry is plus, point of exit is minus. And again, to repeat the same energy concept, inductors can only store and release energy. They cannot produce any energy of their own. Okay. Physical construction of an inductor is simply a spiral coil. You take a current carrying conductor, current carrying capability of a conductor, and you wind it up in a spiral coil. That gives you an inductor. If there is no material present through the center of the coil, we call it an air core inductor. We measure the length of the inductor from the beginning of the first loop to the end of the second loop, to the end of the last loop. And that is noted by lowercase l. That's not a 1, that's an L, okay, lowercase l. So length, and then each loop is a turn, and the number of turns is labeled as N. And then area is the cross-sectional area of the center core. So the equation for a inductor, the physical construction of an inductor, is given by mu N square A over L, where mu is the permeability and is simply the product of mu 0 and mu r. Mu 0 is the absolute permeability, 4 pi into 10 raised to minus 7 . 4 pi into 10 raised to minus 7. Permeability is a measure of the ease with which magnetic flux lines can be established in a material. So mu 0 is basically vacuum or free permeability. And mu r is the relative permeability of a material with respect to mu zero. So mu r is a ratio. It's dimensionless. It's dimensionless. Mu r for air is just 1. Okay, but actual mu permeability in the equation is mu zero times mu r. Mu zero is absolute permeability. Mu r is a material property, meaning it depends on the material that you use. And the r stands for relative. Okay. So if you look at this equation, you can see L, the inductor value, is directly proportional to the number of turns, right? It's directly proportional to the number of turns. It is also directly proportional to the cross-sectional area of that loop, meaning you make one loop, it's a circle, so that area of the circle, the cross-sectional area of the circle of that loop, that gives you the inductor, okay? That's directly proportional to the number of turns and the area, and inversely proportional to the length, meaning the longer the coil, the lower the inductor value. These are some examples of real-life inductors. I specifically like to point out the first two. Very similar in size and construction, but very far apart in the actual values, okay? If you look at the first one, you have a very thick wire versus a very thin wire in the second one. A thick wire allows you to carry very high current. So if you look at that specification, 10 amps is a huge amount of current. 10 amps is huge versus 1.3. Most normal chargers that you use, 1 amp, 2 amps. 1 amp was the standard when it first came out. 2 amps were called as fast chargers. Now it's gone up to like 3, 4, 5 amps. But 10 amps is a huge amount of current, okay? Then few turns, far less turns than the example in B, right? It's quite obvious. You can visually inspect and see. Number of turns in A is low, and number of turns in B is quite high. So the inductance value, again, is directly proportional to N square. So if you look at the inductance here, it's only 10 microhenry versus 1,000 microhenry, 100 times higher, 100 times higher, okay? And finally, there is the DC resistance, 6 milliohms versus 0.4 ohms. 0.4 ohms is 400 milliohms. So 400 versus 6, which kind of makes sense. The thicker the wire, the lower the resistance. Physical, we didn't cover it in this class, but I'm assuming or I'm hoping that you'll came across it in physics, perhaps. Resistance R, physical construction of a resistor, is rho L over A. L over A. L is the length, A is the cross-sectional area. The thicker the wire, the lower the resistance. The thinner the wire, the higher the resistance. Okay. And the resistance matters for inductor. If we go back to the slide, I would like to point out something else. You have this coil, right? This coil, you have two ends of that inductor. If you take the two ends of the inductor and you measure the inductance, you will receive some value. If you place it across a ohm meter and you measure the resistance, you will again receive a value. Because the coil, again, is made out of some metallic material, it has some resistance. Real life wires are not ideal. They will have some resistance. Good quality inductors, that resistance is 5 ohms or less. Lower quality, it's like hundreds of ohms, okay? This resistance is part of that coil. It's part of the material. You cannot separate it out. But mathematically and electronically, we represent it as a resistor in series with an inductor. And that's the last thing I'd like to mention for today. So we cannot separate out this resistor. It is part of that inductor itself, but electrically and mathematically, we represent it as a resistor in series with that inductor. So inductor L will have some value and will have a inductor resistance associated with it. We call this the inductor resistance. Okay, I'll end class here today. We'll see you. I will see you all on Monday. Quiz on Monday as usual, based on Thevenin and Norton network. I won't ask you to completely analyze the circuit. What I am interested in seeing is whether students can set up the problem correctly or not. So I'll give you a bunch of circuits, and you will show me the circuits that will be required to solve for Thevenin voltage, current, and resistance. Okay, so basically setting up the problem, but we will not solve the problem itself. I'll be in my office and available to students between 1 and 2 and 4 and 5. Between 2 and 4, I have a seminar and workshop. All right. I'll see you all later.